Hey, welcome to today's seminar. Our today's speaker is Foivos Fioravantes, and he will tell us about how to hunt a rabbit.
Thank you. So yes, this is a joint work with Thomas Dissot and Nicolas Nice. Both of them were in my previous team in France. And Armender Garhalawat. Some of you may remember him. He visited us for 1 week in the summer. Last time I checked, he was still okay on Saturday night. I hope he's still fine. So, how to hunt a rabbit on a graph? That's a game. We are going to talk about a game. It falls under the general setting of graph searching, where in general it's a series of games where we have an entity, a fugitive, hiding in a graph, and we are interested into locating them, using a minimum amount of resources, usually modeled by cops or searchers or something like that. In our case, we have the hunters and rabbit game. There is a graph. There is an invisible rabbit hiding inside a vertex of the graph. We have a set of hunters and K hunters, which communicate, and in each round, they decide we are going to shoot on these K vertices. They can shoot in less than K vertices if two of them shoot the same vertex, but that makes no sense. So in every round, K vertices of the graph are shot. The rabbit becomes afraid from the gunshot and is obliged to move to an adjacent vertex. Keep in mind, rabbit is invisible. So the hunters have no idea where the rabbit is, but if they do shoot on a vertex which is hiding the rabbit, they do get the information that they managed to catch the rabbit. So the normal question here, the natural question is, what is the minimum number of hunters to achieve this? I don't care if it takes 3 years. We need just to eventually hit the rabbit. And this is the hunter number of the graph, and it is denoted by this h of g. Example. Let's say we have this graph. Remember, the rabbit is invisible, but just to have an example, we are going to be seeing the rabbit there. And let's say that so the rabbit places itself on the graph, and then the game starts. And let's say that the hunters first shoot on these two vertices. Now the rabbit must move. It moves. And it continues. So the hunters, what the strategy I'm showing here will do, they will shoot again on the same two vertices, and the rabbit needs to move. Then they will move on this branch, the hunters, shoot again, twice on the same branch. Why are they shooting twice? Can somebody tell me?
The rabbit might have been
on this vertex here, and if it was initially here, the second time I shoot this vertex, the rabbit is shot. So guess what happens next? The rabbit is shot. Now, I think you can agree with me that there was absolutely no way for the rabbit to survive this, no matter where it was at the beginning. And a way to see it is that using this strategy, the area available to the rabbit does not increase throughout the game. And this is a very important notion. It's the notion of monotonicity, which will be very, it's a main aspect of what we did. And we will see it again, so keep it in your mind. So now we know that this graph has hunter number at most 2. And actually, it is the smallest tree that requires 2 hunters. And that's one paper. The proof for this. Other results as well, but like the proof for this is not one paragraph. Now, pay attention, something important here. It was not mandatory to shoot all the vertices of the graph. This will be, again, important later. Okay, so we saw an example. Let's see another example. How many hunters do you think we need for path of arbitrary length? I take bets. One? Why?
You can start shooting on like even chase and then you go back.
Who told you this? Where did you learn about this? Okay, so
In our school of course.
the easy way to do it is with two hunters. Because if we consecutively shoot two vertices, okay, there I shot twice to take care of the first vertex, and then we can continue like that. And of course, the rabbit cannot find itself from that side of the two shots to the other. So again, monotone strategy. Two hunters are enough. But it turns out that one hunter is also enough for these graphs. And this is mainly due to some trickery that can be done on bipartite graphs in general. So we will see this by like, I put colors to show the bipartition. And there are two options, either the rabbit starts on a red vertex or a blue vertex. Let's imagine it starts on a red. And the strategy of the hunter will be to shoot one by one all the vertices of the graph. So after the first shot, the rabbit is there. We continue, the rabbit moves, tack. Observe that every time we are shooting something, a vertex of blue color, the rabbit is also on a vertex of blue color, and vice versa, the red. So I think you can, it's quite obvious that the rabbit dies here if it started on a vertex of red color. That's important. And this is a monotone way to kill the rabbit, catch the rabbit, if it was in the correct color at the beginning. But what if the rabbit was in the other bipartition? Well, the hunter does not know that, so he will again shoot all the vertices of the graph. But now we have this very annoying thing that the hunter shoots this vertex, the rabbit can go on that vertex immediately, and it's completely safe. And then the hunter has no idea that the rabbit is basically trolling him by coming back to the vertices that the hunter has already shot. But now we are finding ourselves in a very interesting situation, because here, once the rabbit reaches the top, he knows that, okay, the rabbit is not dead, shot. The rabbit is not shot, which means that it started in the other bipartition. So now what it's simple enough to do is shoot again, which changes the bipartition of the rabbit, which is obliged to move in each turn. And now it's the same situation as the initial example that I showed you. So yes, one hunter is enough to catch the rabbit on a path of arbitrary length. And more powerful, it's something in bipartite graphs. We may assume that we know what was the bipartition in which the rabbit started from. Because if we don't, well, we use the same strategy twice, one for the one bipartition and one for the other. Okay, attention. During the first pass of the hunter, the first time he shot all the vertices of the path, the rabbit was trolling the hunter. By that I mean the rabbit was going on vertices that were shot. So the area available to the rabbit was unaffected, meaning that that stage of this strategy was not monotone. Okay. Now, in general, the problem was firstly introduced in a paper called Finding a Princess in a Palace, which was for one hunter and one rabbit, the princess. I can explain it to you later how they managed to model this as in which they showed that any tree has hunter number 1 if and only if it does not contain the tree that I showed you at the beginning as a subgraph. And they observed this peculiar behavior of paths. The game was then generalized in this paper here of Abramovskaya, Fomin, Golovash, and Pilipchuk for many hunters. They computed precise values for cycles, complete graphs, grids, and hypercubes. And the grids and hypercubes results are not trivial. They introduced new tools to get them. They generalized the peculiar behavior of paths into bipartite graphs, what we showed earlier. And they gave the first upper bound for trees, which was subsequently improved in this paper. The dates do not fit. This is a journal paper. That's why they do not fit. And they gave an XP algorithm to compute K, the minimum number of hunters. The XP algorithm is the usual you do by taking many instances of the graph and building the. I will not explain it. Okay, sorry. So what we did now, well, we introduced the monotone hunter number. Well, by monotone, I mean that the area of the rabbit does not increase. Available to the rabbit does not increase throughout the game. Since bipartite graphs are weird, we needed to also introduce the monotone bipartite hunter number, which is only 4 bipartite graphs. We proved a relation between the monotone hunter number and the path width. In particular, we showed that the monotone hunter number is between the path width and path width plus 1. Our contribution here comes towards the left. The right hand of the inequality was already known. And we computed the monotone hunter numbers for split interval graphs, cographs, and trees. And then we showed that the monotone hunter number does not help us because we were able to show that there exist trees for which we can do with 2 hunters normally. But if we decide to need monotonicity, this number goes up arbitrarily, which was not what we expected when we started working on this.
So is the monotonicity the property of the hunters, so that they must shoot in a way such that the area does not increase?
Yes, like... yes, I will define it properly. But yes, that's it. The strategy should take care of the rabbit not being able to come back to where the area that is already dealt with, let's say. And then we have a general positive result. We gave an FPT algorithm for computing the hunter number, parameterized by the vertex count. Questions? Okay, so monotonicity and path width. I will begin by why monotonicity? Why do we care about this notion? Well, usually it's way easier to design monotone strategies because you can always use this argument that the rabbit cannot pass from one side of the graph to the other. And they provide strategies which take polynomial time, meaning that we can place these problems in NP. Also, it is the core argument behind the connection between graph searching games and graph structural parameters such as path width and the tree width. And it is the core idea behind the polynomial algorithm to compute the path width of a tree. So, useful notion. Now, path width of a tree. Now, okay, so about the monotonicity. Now, the classical notion of monotonicity fails in our case. Remember the paths, other problems as well. So we defined a strategy as monotone if it guarantees that the rabbit cannot go on a cleared vertex, and if it does go, it is shot immediately. And the bipartite monotone strategy, where it's the same thing, but we are just assuming that we are doing the second part of the strategy. Like we did the first part to decide in which bipartition the rabbit started from, and we are focusing on the second part, which can be monotone. Now, okay, the bipartite monotone hunter number is at most the monotone hunter number, and for example, for paths, I showed you a monotone hunter strategy, which was with 2 hunters, and a monotone bipartite hunter strategy, which was with 1 hunter. And it is monotone in our definition because we are only looking on the second pass of the shoot. Yes?
exactly means clear? Like if we show
What exactly it means cleared? It means either the vertex is shot on, so it is cleared during a round, either the vertex is shot on that round, or all its neighbors were shot in the previous round. So the rabbit is not on that vertex on that round. Light reminder, what is the path width of a graph? We decompose the vertices of a graph into bugs such that all the vertices appear on every bug, all the edges appear inside the vertices in the bug. And if I look at a vertex and I look the bugs in which it is contained, this induces a path. Okay, I go fast here because I know that most of you know this better than me. Now, how the monotone hunter number is at most the path width plus 1. I repeat, this was already known. Well, the idea is simple, just shoot the vertices of the bug path decomposition. And if we look at this, so this is the first bug, this is the second bug, third bug, gray vertices are the cleared vertices. We continue, like, I think it's obvious that the rabbit can never jump from the other side. And this is indeed a clearing strategy for the graph. Now, the opposite, let's take a clearing strategy and come up with a path decomposition. Well, if we look, so this is a clearing strategy. First, we shoot there. We shoot there again. This clears these two vertices, the 2 and 4, in an indirect way. That's why I put them with the red circle. They are cleared because their neighbors were shot twice. We continue. Now all of the neighbors of 7 were shot, so twice. So he is cleared again. And this is a clearing strategy. And you can see that it is almost a path decomposition. The main thing we are missing is that we have these red vertices that were cleared without being shot. So if we took these vertices would not appear in the path decomposition, and that's a problem. So what we do is we introduce intermediate bugs between each bug of the decomposition, where, for example, the first intermediate bug is between S1 and S2, and it is exactly S1 plus the vertex 2. Then we put exactly S1 plus the vertex 4, and then we go to S2. And it is a bit technical to prove that this is indeed a path decomposition, but I think it's believable. Okay. And do we have questions? Because I'm going to move on. Okay.
So for each red vertex in the bag, you just add them one by one.
Yes.
In this case, 2 and 4.
Yes. And if there are 2 or more vertices that are cleared indirectly in the same turn, I will just need to add more intermediate vertex bugs. Okay, so let's move on. Let's go to the result, which I personally consider the main contribution of this work. When we started doing this work, we tried to answer a previously open question. Find a polynomial algorithm for trees to compute the hunter number of trees. And classically, this is approached by defining a monotone version, showing that any optimal strategy can be computed from a monotone strategy using the same number of hunters. No, sorry, I skipped a step. Defining a monotone version, computing the monotone hunter number, and then show that we can transform any optimal strategy into an optimal non-monotone strategy with the same number of hunters. This is a classical thing. And this is basically what we did. We managed to do the first 2. So we have a polynomial time that computes the monotone hunter number of trees. The third one, we managed to show it is not correct. It's not at all correct. We have trees, arbitrarily many trees, which can have arbitrarily larger monotone hunter number than hunter number. So this is the tree. I repeat, I have put a rabbit here. You don't see the rabbit. It's just there to help understand what's happening. So my claim is that this tree has hunter number equal to 2. I can clear it using 2 hunters if I don't care about monotonicity. The paths are a bit weird, I know. I will explain them as we go on. So how do we clear this thing with 2 hunters? Well, we first start shooting at the top vertex, the root, if you want, and we start shooting one by one this path here until we have forced the rabbit to find itself inside here. If we need to do this twice, okay, sorry, I am bugging a bit. We force the rabbit to be here.
You can also move the thing from the root.
Yes, exactly. That's how. Okay, 2 of them. Sorry, the slides are wrong. Okay. Next, we clear the second path. Now, the length of this path is so big that when I will have cleared all of this, the rabbit will not have enough time to reach the root.
Okay.
Why? I mean, I have the right to have this as long as I want, no? So we clear the second one. If the rabbit was in this path, it is forced to be inside here. And the length of this path is defined in the same recursive way. It is big enough that we can clear the rest. So in the end, we have cleared until the end there, and the rabbit did not have enough time to reach the root. And then we go inside here and we clear this first branch. And the rabbit, worst case, it is right next to, but now we have to shoot. What's happening here? Why is this not working now? Okay. Now I am obliged to shoot the vertex at the top. I am not obliged to shoot the vertex at the top every turn. I can alternate. So one red vertex, let's say that the vertex at the top is red, I only shoot it during the red turns, and during the blue turns, I can use 2 hunters inside this path. It's a bit more tricky than I remembered. Okay, but the main idea is this. The main idea is that I allow the rabbit to recontaminate a path, which is so long that it allows me to deal with the rest of the graph, basically. If this is a bit unclear, I will gladly discuss this with you later. Now it's clear for me as well. Now, so sorry for that. Now, why this graph has monotone hunter number more than k? Now, this is the same graph. It's just that I am also looking inside those triangles. And the idea, what we did manage to prove is that when so let's say that we have a monotone strategy that clears the graph. There is going to be a moment where the first branch is cleaned. If it's a winning strategy for the whole thing. So on that moment, there are going to be 2 branches that have never been shot. If not, then the strategy is not monotone. We can prove that the strategy is not monotone. So there is a moment where this happens. And from that point onward, we are kind of obliged to keep shooting on this vertex during the proper parity of turns, either red or blue, according to what. And then we go on and we look at this. This is the first branch among the 2 that were never shot that is going to be cleaned. Again, the same argument. It contains 2 branches. One branch that is going to be the first one that is going to be cleaned, and 2 that have never been shot. From that point onward, we need to protect that vertex. And we continue like that. And I can have this be as big as I want to require as many layers here as I need to have an arbitrary number of hunters during one turn, at least one turn. Okay. Finally, the exponential kernel we gave for the vertex cover. The slides are not going to be nice. So we have this theorem that we can have a kernel of this size where T is the vertex cover number of the graph. How do we do it? Well, there are two arguments. First, the vertex cover itself is an upper bound on the Hunter number. Just shoot 2 times on the vertices of the vertex cover. It was either on those vertices or on the independent set. Now it's shot. The second argument is a bit more tricky. What we do is we basically take all subsets of the vertex cover. We look at their neighborhood in the independent set. The sets here that are looking exactly on the subset of the vertex cover. And we get rid of, and if these are very big, we get rid of more than a part of them. Figure makes it easier. So I have my set here, a subset of the vertex cover. These are its neighbors inside the independent set. If here I have all the possible edges, it's a complete graph here between these two. And the claim is that I can basically get rid of more than, if here I have more than k plus 1 vertices, I can get rid of the extra ones. G is the initial graph, H is the graph without the vertices I got rid of. Now, if I can clear the whole graph with k hunters, I can clear the subgraph with k hunters as well. This was actually proven, it's a lemma. Now the opposite side is we need also the other direction, which is a bit tricky to show. No, it's tricky to do. So instead we do the negation of it and so instead we will show that if the Hunter number is strictly greater than k, then also the Hunter number for the small graph is strictly greater than k. Now let's assume that the Hunter number is strictly greater than k in G. It means that the rabbit can survive k hunters in G. It means that there is a trajectory in G, which at the end finds the rabbit somewhere alive. Now, while this trajectory stays in H as well, do the same thing. There's no problem. If at some point the trajectory visits the vertices that we want to get rid of, well, there is an edge here, but there is also an edge like that. So instead, we say to the rabbit, go to one of those vertices. And here we have k plus 1 vertices and k hunters. So there is at least one vertex here that is safe during that round. And that's where we tell the rabbit to go. And then we continue following the trajectory that survives G. Okay, so this managed to give us a surviving trajectory for the rabbit in H, completely contained in H. And now what remains to be done is look at all the subgraphs of the subsets of the vertex cover. And for each one, keep at most k plus 1 vertices. And that's basically our kernel. This, combined with the XP algorithm that was shown in the previous paper, gives us an FPT algorithm for our problem. Okay. Now, conclusion. Open questions. Polynomial algorithm to compute the Hunter number for trees. It's still wide open. It's some could say now it's more open than it was before. Basically, because the main tool that is used for those things, we showed that it does not work here. What is the complexity of computing the hunting number? This is completely untouched. The monotone Hunter number, which we introduced, is between the path width and the path width plus 1, and the path width is not approximable. So we know that up to constant factor, right? So we know about the hardness of the monotone Hunter number, but nothing about the Hunter number. And then it will be also nice if we saw some structural parameter which corresponds to the hunter number, the way that tree width corresponds to a graph searching game or path width, similarly. And that's it. Thank you. Any questions? Yes?
So the main difference from tree width is that there's cops and robbers game, right?
Yes.
The main difference is that they don't know where the rabbit is.
No, the tree width game, the rabbit is visible, yes. So this is closer to the path width game, where the rabbit is invisible. The main difference is that the rabbit is obliged to move in every turn. That's the key difference.
If you play the cops and robbers, you have that tree, and you know in which branch the rabbit is. So then you know where to go. It doesn't matter if he moves or not. So I actually explore that tree and kill it.
Yes. So since the rabbit is invisible for us, it is closer to the game that corresponds to the path width, which has an invisible rabbit. And the main difference with that game is that in that game, the rabbit is not obliged to move.
But then it's probably just plus minus 1 factor difference, right? Oh, I see.
The fact that the rabbit is obliged to move completely changes the behavior of the problem. This whole bipartite trickery that happens basically because the rabbit is obliged to move bipartition every turn. This does not happen if you don't oblige the rabbit to move. I heard there is something on another question. No?
But then it's the number of hunters that is needed is less than if you don't move the rabbit.
There, the number of hunters that is needed is exactly the path width of the graph, +1, I think.
Okay.
So we are between path width and path width +1, and we don't know which.
I said.
Deciding which one.
I guess so it's time to speak again.